Welcome to Week 1, Python Fundamentals. These videos were recorded using an older version of Anaconda with Python 3.7. For these courses, we're using Python 3.8 and Anaconda 2021.05. I have updated the course notes to reflect these changes. I have not bothered to update the videos unless there has been an actual change in the behavior between Python 3.8 and the older Python 3.7. So when you see references to Python 3.7, don't worry about that. Whatever I'm saying in that part of the lecture video is still true of Python 3.8. Now, our assumption about you for this course is that you have previous programming experience, but it may not be in the Python language. So we're going to start from the basics of Python, but we're going to move forward at a pretty brisk pace to try to cover as much Python as we can in 6 weeks, relevant to obtaining, organizing, and analyzing data. Okay, so Python is what's called a multi-paradigm language. It can be used as an old-fashioned top-down, procedurally oriented language, or it can be used as an object-oriented language. Its main benefit is that it's much easier to write compared with more traditional procedural and object-oriented languages such as the C language, the C++ language, Java, or various others. So it's really excellent for rapidly developing applications. On the other hand, for very large projects involving many programmers at once working on the same code, possibly Python is harder to maintain than these more formal and rigid languages like C++ and Java. Python is interpreted, which does make it slower than compiled languages. Also, its flexibility in how it manages objects in memory turns out to make it slower than compiled languages as well. In fact, if you write some simple sorting algorithms like, let's say, selection sort or quick sort or merge sort, and test those in Python using something called lists versus in C++ using arrays or vectors, you'll discover that the C++ is about 5 to 10 times faster than the equivalent Python code. So what does efficiency mean in the end? Efficiency can mean how quickly can you get the work done, in which case Python definitely wins almost always. It can also mean how quickly does the working program run once it's finished, in which case languages like C++, Java, C, and so forth win. But for many tasks, being able to get something working quickly is your goal, and so Python is very good at that and growing in popularity at a very brisk pace. By the way, although when you look at Python documentation, you'll see that it has this sort of cute stylized snake as its icon. It actually is named for the Monty Python British comedy troupe, not for the snake. And documentation about Python often contains little embedded examples from Monty Python skits. Python is an open source project. Everything about Python is available for you to look at the implementations of. It was originated by a fellow named Guido van Rossum, who has been designated the benevolent dictator for life of the overall Python language and environment. This is abbreviated as BDFL. And you'll discover that various other people are BDFLs of important modules or libraries within the overall Python environment. In fact, Wes McKinney, who is the author of the primary textbook that we're using for the course, is the originator of the pandas module and is the BDFL for pandas. There are 2 versions of Python out in the world, version 2.x, which is fading in popularity very rapidly, and version 3.x. We will be using, in particular, Python 3.7. You should go out to the web and install Anaconda 2019.10, unless something more recent has come out in just the last couple of weeks, in which case, by all means, install that most recent thing. This Anaconda package incorporates not only the Python language itself and its base libraries, but also includes a variety of additional add-on modules and libraries too that we'll be making use of in this course. So if you download and install Anaconda, you will find that that Anaconda development environment incorporates most of the editors, interpreters, integrated development environments, libraries, and modules that you might need for the duration of this course. I posted an announcement that illustrates how to install Anaconda on your system. You can install Anaconda both on a Windows 10 machine and on a Mac machine. For those of you who are using Macs, please take a look at the announcement that I posted about using Anaconda and Python on Macs. Okay, so once you have installed Anaconda on a Windows 10 machine, you will have an Anaconda prompt icon in your Start menu. You can also put the Anaconda prompt in the taskbar at the bottom of your screen. On a Mac, you can simply start an ordinary terminal. Now, when you launch that Anaconda prompt or ordinary terminal on a Mac, here's what that will look like. All right, so for me, I get this window that says base and then my home directory path name on Windows. And I'm going to run idle, which is the simplest integrated development environment available for Python. Now, I like to use idle for my lectures because it has no screen clutter at all. There's no menus, there's no icons, there's no tiny fonts and tiny symbols. It makes it very easy for me to present things. You will very likely find that something like Jupyter Notebooks or the Spider integrated development environment or PyCharm or something along those lines is more convenient for you to use. But I'm going to start with idle. And here is what I get when I run the idle command. What I get is a Python shell. My version here is 3.7.4. You may have something slightly more recent than that, but actually for our purposes, anything more recent than 3.6 is fine. The 3 greater than symbols is the prompt that indicates that the Python shell is waiting for me to type some Python language statements. All right, so let me do something really easy. Let me say A gets 123. So this creates a variable named A and sets up that variable A to refer to an integer value of 123. If I just type a variable name at my prompt, what Python does by default is to display the representation of the value that that variable refers to, which in this case, of course, is the integer 123. I can quit from the shell by typing quit. Now, here's an annoying thing. You may be able to tell that quit is highlighted in purple in my shell, but at this point, if I just hit the enter key, Python gets angry at me and says, no, you have to use quit with parentheses to get out of the shell. It turns out that quit is a function, and you have to call the function in order to quit from the shell. This is very annoying, but one of those things that you just have to get used to. Now, when I do this, I will get asked for confirmation. I get told your program is still running. Do you want to kill it? And actually, I don't. I'm going to click cancel here and remain in my shell, because if I did actually quit and restart idle, I would have to change the shape of the shell window to make it fit neatly in my screen for video purposes. All right, so I'm just going to remain in my shell at this point. Now, anything from a pound sign or sharp sign to the end of a line is treated as a comment. And interactively, these things are not too useful. You can use them, but they don't, since you're the person typing the code, it's sort of silly in a way. But to illustrate, I can say A gets 123, as I already did, and I can comment A is an int variable. All right, so notice that that's highlighted in red in my idle shell. X gets 2.7, causes X to be created as a variable referring to what's called a float value. As another example, I'm saying S gets high. And this is what's called a stir variable. All right, so int, float, and stir are data type names for values in Python. And I can't usually bring myself to call something a stir, so I will typically call these things strings. And you'll just have to understand that what I'm talking about there is the Python stir data type. B gets true, sets B to one of the two possible Bool values, either true or false. Notice that that's capitalized. Lowercase true is simply an error. It's not the value true in Python. You may notice that I've been pronouncing this single equal sign as gets. That's in order to distinguish the single equal sign from the double equal sign that does a logical comparison for equality. If I ask whether A is equal to 123, that expression gets evaluated and the result is then displayed by my shell. The result of that comparison is true. All right, so to make clear what I'm talking about, I will tend to pronounce the single equal sign as gets and the double equal sign as is equal to. If you call both of these things equals, that is, if you say A equals 123, A equals 123, how verbally, if you're talking to someone on the phone, can you tell apart what you're talking about here? So I use gets and is equal to for consistency. Okay, so I've created a bunch of variables here, A, X, S, and B. We should talk about what you can legally name your variables. And for that matter, this will also apply to function names and class names that we'll be creating later on. The rule is that the first character has to be either a letter or an underscore character. A letter can be either uppercase or lowercase, and upper and lowercase letters are distinct in Python. All right, so if I say A in caps gets 3, that is a different variable from the A in lowercase that I had created previously. All right, so little a is currently referring to the int value 123. Capital A is referring to the int value 3. Following that first character, you can have 0 or more additional letters or decimal digits, that is, characters between character 0 and character 9, and underscores. 3 is not a legal variable name, thank goodness, because it does not start with a letter or an underscore. It would be fairly catastrophic if I could say 3 gets the string high. But underscore 3 is a legal variable name, and so here I'm saying underscore 3 gets the value 9. That's legal. It's possibly a bad idea, but you can do that if you'd like. Underscores are often used to separate the parts of a variable name into different words, for example. So I can say has 3 apples separated with a couple of underscores to make it more readable, and perhaps that value is true. All right, so has 3 apples is a legal variable name, and it refers to true. We've already talked about the fact that upper and lowercase letters are distinct. If I say little a gets 2, little a, big A gets 3, big A gets 4, big A gets 5, I have created 4 separate independent variable names here, each of which is referring to a distinct value. Okay? cm per IN is centimeters per inch. Turns out for any of you with any kind of engineering or physics background or math background, luckily for we in the non-metric United States, it turns out that by definition an inch is 2.54 centimeters. So it's therefore easy to convert any kind of distance from the metric system to the English / Americish system. You cannot use things like dollar symbols in variable names. If I try to say $con, some kind of conversion factor is 2, I get yelled at. Now, a dollar symbol is valid in some languages. For example, in Perl, the dollar symbol is used to indicate that a particular variable is referring to a scalar value. Interestingly enough, if I were teaching a course about a very popular, easy-to-use interpreted language about a dozen years ago, Perl would have been that language. But ultimately, Perl sort of collapsed under its own weight. So it's sort of interesting to me, being a bit of an old-timer, a dozen or so years ago, people would have said, oh, you can learn Perl and have a great job forever. And now it's more or less gone, and we're learning Python instead. My guess is, because of the simplicity and clarity of Python code, that Python is going to have a much longer length of life than Perl turned out to have. But it's a useful lesson to understand that languages don't necessarily last forever. All right, for the last example here on slide 9, sometimes people will attempt to use hyphens in variable names. Unfortunately, the hyphen is actually the minus sign, the subtraction operator, and so that won't work either. If I say centimeters per foot is 30.48 and hit the enter key, I get yelled at by the interpreter. Okay, I expect most of you, although unfortunately I can't ask you and see you raise your hands here, I expect most of you have got some Java training, perhaps some experience in C++ or C# or something like that. And you're used to the idea of a variable having a data type associated with it. So we would have int variables or double variables and so on. That's not the case in Python. In Python, a variable is simply a reference to an object. And the object is the thing that has the data type associated with it. The variable can be changed to refer to different objects, and those different objects may have different data types. So here on slide 10, if I say I gets 123, what I'm really saying is it becomes a reference to the int object 123. I can use a built-in function type with the variable name I to find out what the data type is of the object that I currently refers to, and I get told, okay, that thing is class int. But if I say I gets 2.7, whereas in something like Java or C++, that would truncate the fraction and put a value of 2 into this int object I. In Python, what happens is that I is simply changed to refer to a float object instead. And so now if I ask for the type of I get told that I is now referring to a float object. We'll see in a little bit that a float object in Python is the same as a double object in C or C++ or Java. If I say I gets high in quotes, that's fine, and the type of I is now stir. So I is now referring to a stir object, a string object. By the way, you may have noticed that I've been using either single quotes or double quotes to create these stir objects. I'll have more to say about that a little bit later. Okay, so in Python, a variable name simply refers to an object, and it is the object that has the value and an associated data type. Low-level scalar data types in Python include int, and in Python these are actually arbitrary precision, so ints can be arbitrarily large in either a positive direction or a negative direction. Float in Python is a 64-bit double precision value, so float, as I suggested, is like double in C or C++ or Java. Stir, for strings, contains Unicode UTF-8 character strings. Now, UTF-8 is probably the most common character set for web page development, and fortunately for us, being in the United States, UTF-8 contains within it the ASCII character set as a 7-bit subset. So all of the characters that we can type on our keyboard will fit within a stir. There are also a so-called bytes data type, which is for binary data. We're not going to use that, but I do want to mention it in case you encounter it. The Bool data type, for Booleans, only has two possible values, either true or false. And these do have to be capitalized. All right, so true with a capital T is Boolean true, and false with a capital S is Boolean false. True without the capital T is some kind of variable name, but there is no such variable existing, so I get told, all right, true is not currently defined. Finally, the special value none with a capital N has no value, or a null value or an empty value or whatever. If I set a variable to none, that implies that the variable is this is sort of awkward. Technically, the variable is referring to the special single value none, but we think of it as referring to nothing. Alrighty. Okay, so we've got int values like 123 and 5 and so on. We've also got float values like 2.7 and so on. We'd like to know how to do computations with these things, so let's take a look next at the arithmetic operators that Python provides. These are similar to, but also different in interesting and potentially annoying ways from the operators that you may already be familiar with from something like Java or C++ or C. I've shown these here on slide 12 in precedence order from highest precedence to lowest precedence as we go down through the rows here. So the double star has the highest precedence. Plus and minus, these are the unary plus and minus signs. These have the next highest precedence. Then star, slash, double slash, and parentheses, which stand for binary, multiply, divide, floor divide, and modulus. Those are at the third level of precedence among the arithmetic operators. And finally, the binary addition and subtraction operators, plus and minus, have the lowest precedence. Okay, so every operator at the same level has the same precedence as each other, going from star star, which is the highest precedence of these, down to binary plus and minus, which are the lowest precedence. We can, as won't surprise you, use parentheses for grouping, either to try to clarify what we're doing or to override the normal precedence of these operators. Okay, so the star star operator is an exponentiation operator. And if I say 2 star star 10, 2 to the 10th is the computer scientist's notion of 1K. It's the value 1024. 2 to the 20th is 1 meg. 2 to the 30th is 1 gig, and so forth. Notice that if I take an int to an int power, the result that I get is also an int. If I take an int to a floating point power, this is 2 to the 0.5 power, which is going to give me the square root of 2. The result that I get is also a float. Okay? Now, 2 to the 100th power is fine, no problem. Remember that Python ints are arbitrary precision, so I can even compute 1234 to the 1234 power. This is going to go flying off the top of my screen. Well, okay, this version of the idle shell just tells me that there's squeezed text here of 62 lines of output. Let me unsqueeze that. Here is an accurate, well, let me see if I can display this thing. Come down here. Here we go. So here is an accurate representation of 1234 to the 1234 power. Whoops. Guess once I let go of that scroll bar, it doesn't like to show me the whole thing. Okay, so this goes on for, looks like about 3 slides worth of output. And that is a correct representation of 1234 to the 1234 power. Now, a negative subscript will give me a floating point result. 2 to the minus 100, of course, is the same as 1 over 2 to the 100th power. So here I get 7.8886 and so forth to times 10 to the minus 31st. All right, so the star star has the highest precedence of the arithmetic operators. The next highest precedence operators are the unary plus and minus. Now, plus 2 simply has the value 2. In real life, you will never see anybody use the unary plus, except for this example in this class. It's basically just in there for symmetry with the unary minus. Minus 2 has the value negative 2, obviously. From Java or C or C++, you may recall the increment or decrement operators, where if you said something like minus minus of a value, that would decrement the value by 1. But Python does not have these increment or decrement values. So minus minus 2 in Python is treated as the negative of the negative of 2. And so that's just 2. Okay? The next highest precedence operators are the so-called multiplicative operators. So if I say 2 times 3, I get a 6. Or 6 divided by 4, I get 1.5. Notice that in Python, division of one int by another produces a float. In fact, this is always true. Division always yields a float in Python. Even if I were to say something like 4 divided by 1, I don't get the int value 4. I get the float value 4.0 from that division. Okay, now the lowest precedence of the arithmetic operators are the binary addition and subtraction. If I were to say 7 plus 5 times 3, then by precedence rules, the 5 times 3 would be evaluated first. That would give me 15 plus 7 is 22. I can use parentheses, though, to override that usual precedence and cause the 7 plus 5 to be evaluated first, and the result of that multiplied by 3 to get 36. Okay? Similarly here, in the next example, if I say 12 divided by the quantity 6 minus 1, that's 12 fifths, which is float 2.4. Okay, so in addition to star for multiply and slash for divide. The other two multiplicative operators that are at the same level of precedence as multiplication and division are the percent sign, which is modulus. This gives you the remainder after division. And the double slash, which is what's called floor division. And this does a truncation to an integer in the direction of minus infinity. So let's take a look at these examples and talk about them. If I ask for 11 mod 3, well, if I were to divide 11 by 3, I would have a remainder of 2. And the modulus operator gives me that remainder. Now, if I take minus 11 and ask for mod 3, the remainder after division there would be a minus 2, but the modulus always has to be a positive number for Python. So we add 3 to that remainder, and we get a modulus of 1 rather than minus 2. If we were to compute 11 divided by 3, this is going to give us a float result, 3.666, etc. 11 floor divide by 3 gives us the integer resulting from truncating that fraction part in the direction of minus infinity. So 11 floor divided by 3 gives me a 3. Now, why was it important for me to mention that this is being truncated toward minus infinity? In C and C++ and Java, if you do an integer division, the truncation of the fraction is towards 0. If I were to do a minus 11 floor divide by 3, I might expect, if I had a C, C++, Java kind of background, to see minus 3 as the result. But in fact, what I'm going to get here is a minus 4. Why is that? Okay, so minus 11 divided by 3 is minus 3.666, etc. And if we truncate that fraction toward negative infinity, the integer that we get to is minus 4. All right? So this takes a bit of getting used to if you're a Java or C or C++ person. All right, so those were mostly examples involving ints. Let's take a look now at examples involving float operands. 2 to the 10th power, we saw if both operands are ints, is the int 1024. But if either of the operands is a float, 2 point to the 10th power, for example, then I get a float result. That's also true if I say 2 to the 10 point power. 2.0 to the 100th power works fine. But recall that in Python, float values are restricted to 64-bit floating point format. And so if I try to compute a floating point exponent that's too large, like 1234.0 to the 1234 power, this is going to cause an overflow floating point error, and I get yelled at. Overflow error, result is too large. There's also a limit to the number of digits of precision that we get when we're doing float computations. Recall this value that we got for 2.0 to the 100.0 power. Okay, if I compute the integer version of that, 2 to the 100th power, notice how many digits of precision that I get. However, if we take a look at the floating point result, I only get 16 digits of precision stored within that float. The trailing part of that value is lost. You always need to think of a float value as being a reasonably close approximation to the true value that you're trying to represent. Here on slide 17, we're showing some examples of the floor division using float operands. We get float values as a result, but the fraction part of these results are 0 always. I'm not going to bother showing these examples in my shell. Let's go ahead and move on to looking at strings. Now, in Python, you can represent a string, a str, I should say, by typing double quotes around a sequence of characters, or by typing single quotes around a sequence of characters. Why should we care? Well, of course, the single quote and the double quote themselves are characters. You might want to represent a single quote as part of a string. You can do that by using double quotes around the string containing a single quote. So here I've got a string of 5 characters, capital D-O-N apostrophe T. Or likewise, I could use single quotes if I want to represent a string containing double quotes. All right, so here I have the string hello, the double quoted string hello, as part of the string that I want to represent. You can use the plus operator in strings, and what it means is concatenation. Okay, so if I say hello in single quotes plus hello in double quotes, I get the concatenation of those two things, which is just hello, hello. Or in the example shown on slide 18, what I'm doing is I'm creating a string in double quotes containing single quotes within it, and I'm concatenating that with a string in single quotes containing double quotes within it. All right, so I've got hello in single quotes being concatenated with hello in double quotes. Now, the internal representation of that string uses single quotes to contain the whole sequence of characters. And because the concatenation of those two strings actually contains individual single quotes as part of the string, you'll notice that I have this notation backslash single quote to represent a literal single quote. We'll see more about using the backslash inside of strings to represent special characters like tabs and new line characters as well. The times symbol for strings means repetition. So if I say ASDF times 3, I get ASDF, ASDF, ASDF. If I wanted the sequence of digits 0 to 9 repeated, let's say 4 times, then I can just say quote 0 to 9 quote times 4, and I get that sequence of digits repeated 4 times. All right, now in addition to using single quotes to contain a string or double quotes to contain a string, it turns out I can use triple single quotes or triple double quotes to contain a string. One advantage of using either triple single quotes or triple double quotes is that you can now have multiple line strings just contained between one set of triple quotes. All right, so if I say quote, 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 this is the first line of a 4-line long string. Okay, you'll notice that I didn't get a prompt. The shell just let me continue typing this thing. I now have a 4-line long string, and internally, each place where I hit the enter key, Python is going to represent where I hit the enter key as a so-called new line character. All right, so each of these \n things here is a new line character. And if you're familiar with Java or C or C++, you will be familiar with this \n notation. Okay, so you can use whichever is the most convenient for you. You can use a pair of single quotes. You can use a pair of double quotes. You can use a pair of triple single quotes or a pair of triple double quotes to contain your string. Internally, these 4 strings shown on slide 20 are all represented the same way and are therefore equal to each other. In fact, I've already shown you the equality test, so we can demonstrate that this is true. If I say hello in single quotes, and I ask whether that is equal to hello within a pair of triple quotes, triple double quotes, I'm told, yes, that's true, though they're the same thing. Okay, so we have now seen examples of the int, float, and stir data types and values, and also how you can use some arithmetic operations even with strings, namely the plus for concatenate and times for repetition. The fourth scalar type I've already actually talked about. The Bool type, the two legal values are true with a capital T, false with a capital F, and if you misspell them, Python will think you're trying to create or access some kind of variable name or function name instead. We talked about the precedence of the arithmetic operators. I also want to mention the associativity of these operators. That is, whether they group from left to right or from right to left. It turns out that all of the binary arithmetic operators group from left to right, with the sole exception of the exponentiation operator. So if you're used to the left to right associativity of the arithmetic operators from Java or C++, the same associativity rules apply for those operators that you're already familiar with. But in Python, we also have this exponentiation operator, and it groups from right to left. That means that if you compute 2 star star 3 star star 2, you might glance at that as a C++ or Java programmer and think, oh, okay, I get it. 2 cubed is 8, 8 squared is 64, and you evaluate that and you get, oh, 512. What's going on here? Well, the reason is that this is actually evaluated as 2 to the power of 3 to the power of 2. Okay, so in other words, 3 squared is 9, and 2 to the 9th power is 512. That is half a k. So it's the same thing as 2 to the 10th power divided by 2. Okay, so just remember this one exception, that star star evaluates from right to left rather than from left to right, as all the other binary arithmetic operators do. Python provides assignment operators very similar to those you're familiar with from Java or C++, assuming that you know one of those languages. For example, if I have a variable a referring to 2, and then I create a variable b referring to 4, and I say a exponentiation gets b, this is equivalent to saying a gets a to the b power. So a is going to end up containing the value 16 as a consequence of that. And then later if I said a minus gets 5, that would be the same as saying a gets a minus 5. And so now a is going to refer to the value 11 rather than the value 16. Okay, so that gets us to the conclusion of talking about variables in Python and also talking about the scalar data types, int, float, stir, bool, and the special value none. We've also discussed arithmetic and these somewhat related assignment operators based on the arithmetic operators. In the remainder of this material, we're going to take a look at collection types, particularly the list data type. And we're also going to see that a stir can be thought of and used as a collection.